Okay. Last time we discussed the uniform continuous function, and today we'll be studying the two greatest theorems on continuous function, the intermediate and extreme value theorem. Okay, so first, the intermediate value theorem. Suppose we have a continuous functions, and this function is defined on some closed and bounded interval AB. Then f takes on all values between f of a and f of b. So this is the intermediate value theorem. Sounds very obvious. Okay. Now, before we try to prove this, I want to rule out some trivial cases, because such as, what if f of a equals to f of b? So if f of a equals to f of b, then the all values between f of a and f of b is just f of a itself, right? And in that case, the intermediate value theorem is always true, because at this endpoint, then you can find the function values at this endpoint is just f of a. So there's nothing to prove. So, well, therefore, from now on, we are going to assume that f of a and f of b, they are two different numbers. Moreover, I'm going to assume that f of a is greater than f of b. So, yeah, so without loss of generality, so we assume that f of a is greater than f of b. Okay, now choose any number. Between these intervals, f of b and f of a. Now, I'm going to show you that there is a point between a and b such that f of that point is m. To do that, first I will need to define a subset such that f of x is greater than m. So what is this? In picture, well, we are assuming fa is greater than f of b. So, like, say that this is the graph of y is f of x, and this is y is m. If this is my m, then this set v must be the interval such that whose function values are greater than m. So must be these union of these highlighted intervals, right? This green highlighted interval should be your v. Okay? Because on these intervals, the function values are greater than. Okay, good. Well, obviously, this set V is a subset of A comma B, which is closed and bounded. Also, you have to note that this set V is always a non-empty set. Is non-empty. Why? Because Well, m is a number between f of a and f of b. So there, that means this point a, it should always be included in this set V, no matter what. Okay. So this is a non-empty set for sure. So, okay. So this set V is a non-empty set, and this set V is bounded above and bounded below, because this is a subset of the closed and bounded interval. And remember, because of the least upper bound theorem, or a least upper bound axiom, the every bounded and non-empty set must have the least upper bound. So the least upper bound, which I will call C, exists. In this picture, this point must be the C, the least upper bound. Okay. Okay. So now what? Yeah. So we know that we proved the existence of this point C, and what I'm going to show is the function value at this point must be precisely n. If I can show that, then this proves the intermediate value. Okay. There is very typical trick to prove that some number equals to the other number. So that is proof by contradiction. So, well, we're going to assume two things. We will assume that f of c, the function value at this point is less than m, and we're going to derive a contradiction. And well, once you're done about that, now then we're going to assume that f of c is greater than m, and we'll derive another contradiction. Then the only remaining option would be f of c equals to m. Okay. 네. 예. FC가, 그러니까 fx가 이제 함수값이 m보다 스트릭트리 큰 녀석들만 이제 잡아놓은 게 이거 V잖아요, 그렇죠? 이 녀석의 그럼 리스트 어퍼 바운드는, 그러니까 리스트 어퍼 바운드는 이 집합에 속해 있을 필요는 없는 거죠, 그렇죠? 네. 그렇죠. 네, 맞아요. 네. 네, 좋은 질문이에요. 오케이. m is greater than f of c, so m minus f of c divided by 2, this is a positive number. And for this positive number epsilon, I'm gonna take advantage of the definition of continuous functions. Since f is continuous at c, there is a positive real number delta such that if x is in the delta neighborhood of c, for any x's that is in delta neighborhood of c, then the function values f of c minus f of x is less than epsilon, right? So this is our definition. But I will rephrase this inequality like this. F of c minus, well, f of x lies between f of c minus epsilon, f of c plus epsilon. So these two inequalities are both true, but I want to focus on this inequality. So what if I plug in this epsilon into here? Then it's going to be m plus f of c over 2. So this is simply the midpoint between m and f of c. But, well, m is assumed to be greater than f of c. So this whole thing must be also less than epsilon. Sorry, less than m. Sorry, yeah, less than m. So, okay. Okay. Now, why is it a contradiction? Oh, yeah, good. Okay. So this is C, and this is C minus delta, and this is C plus delta. And on this interval, the function values are less than m. This is okay. We know this. And why is it a contradiction? Oh, because just choose any number on this side of interval, which I will call x0. Choose x0 from C minus delta to C. Then, because on this interval, function values are always less than m, therefore, the function value at this point also must be less than m. And is it a contradiction? Yeah, right. Because, so, x0 is an upper bound of v. Why? Okay, that is easy because C was the least upper bound of V, right? So that means beyond this point, the function values are always less than equals to m, right? So beyond this point, the function values are always less than equals to m. And also, so on between here to there, every point on this interval, their function values are also less than m, right? Therefore, x0 can be our new upper bound of set V. Right? Right? Yeah? Okay. And is it a contradiction? Yeah, absolutely. Because C was assumed to be the least upper bound. So that means any other number less than C cannot be an upper bound of V. But as you can see from here, we were able to find a number, which is x0, and that was less than C, and that is still an upper bound. And this is a contradiction. Okay? All right. What's next? Now, we suppose f of c is this time. Yeah. Now we suppose that f of c is greater than m. Well, likewise, we're going to choose our epsilon to be f of c minus m over 2, which is still positive. And for since f is continuous at c, so that means I can find another real number delta, possible real number delta, such that if x minus c is less than this delta, then f of x lies between f of c minus epsilon and f of c plus epsilon. Okay, right. Okay, and I want to plug this epsilon into here. Then it can be written as f of c. So this is f of c plus m everything over 2. So again, this is the midpoint between m and f of c. And so this is greater than m, right? So in other words, on this interval, so if x is in the delta neighborhood of c, then function values on this interval, they are all greater than n, right? Now, this time we choose x0 from c to c plus delta. Then, well, as before, just like before, f of x0 is greater than m. Why? Because on this interval, function value was known to be greater than m. And is it a contradiction? Yeah, this is also a contradiction. Why is that? Because, well, this V was collection of all such points whose function values are greater than m, right? So therefore, beyond this point, beyond C, there should not be no such a point whose function values is greater than m, right? But however, I was able to find a point which is greater than C, and the function value at this point is still greater than m. This means C main is not an upper bound anymore. And this is a contradiction. Okay. C, B, and so therefore, f of C must be, and this proves the intermediate value here. Okay, yeah, I really like it because, well, yeah, there are so many freshman textbooks. So there are so many textbooks on the freshman calculus in the market, and most of them they are just merely introducing intermediate value theorem. But a few of them they try to prove the intermediate value theorem. But what I really like most about our textbook is they actually give you very nice proof of the intermediate value theorem. Okay, all right. Okay, what is a big deal on the intermediate value theorem? Well, intermediate value theorem is, of course, important, but the Professor Lex and Professor Torrell, they are basically the applied mathematicians. So they are trying to give us very nice example on the on applied mathematics, finding the root of a given equation. Finding a root of an equation. Suppose that you have some equation, then being able to exactly find the root, location of the root is almost always impossible. So therefore, for these cases, all we need to do is just approximate the location of the root. Then how do you approximate the location of the root? There is very interesting method, so-called the bisection method. So it goes like this. X squared minus 1 over x minus 3 equals to 0. So basically, you're supposed to find the solution of the degree 3 polynomial. Well, yeah. Technically, we have the equation formula for the degree 3 polynomial, but yeah, I don't like it. I just gave it up memorizing. So in this case, how would you find the location of the root of this equation? We're going to put the left-hand side of this equation to be f of x. And on this interval, so this function is all, well, obviously this is continuous function on this interval. Therefore, I will need to apply, I can apply the intermediate value theorem. So we have these two endpoints, 1 and 2. So if you plug in the function values at one endpoint, then, well, f of 1 is 1 minus 1 minus 2, which is negative. And f of 2 is 4, 1, which is still positive. So evaluating your function values at these two endpoints, and if their signs are different, then that means between these two endpoints, there must be one such a loop of the equation. So, so therefore, our next guess would be the midpoint between these two endpoints. So in our case, f 1.5, I will evaluate our function at this point. Now this requires a little bit of calculation, but yeah, turns out to be, which is still negative. So, and therefore, the root must be somewhere between 1.5 and 2. Therefore, our next guess is the midpoint of these two endpoints, which is 1.75. And again, it turned out this is still negative, and this is positive. So we know the root is somewhere between these endpoints. So we're continuing the procedure like this. Now we can actually squeeze the intervals that might contain the root of your equation. And I think, yeah, this is just very easy, one of the easiest applications of the intermediate value theorem, but I still believe this is one of the best methods that we can get. So especially on finding the root of the equation. Why? Because its conversion speed is as fast as an exponential function, right? So this is super fast approximation. This is called the bisection method. All right. And okay, so that was about the intermediate value theorem. Now we are about to study the extreme value theorem. Well, every continuous function defined on closed and bounded interval must attain the maximum and the minimum at some point on this closed and bounded interval. So this is the extreme value theorem. Well, yeah, I remember, yeah, I was introduced to this theorem when I was a high school student, but I was only able to prove this when I was like junior in undergrad, junior and undergrad. So they never they never bothered to give us the proof of the extreme value theorem. But we do. Well, just consider any two random intervals. They may or they may not intersect each other, but we can still consider this proposition. Consider the following proposition. Yeah. So this which we will name, which will be namely P. There is a point in interval I such that for or y in J, f of x is greater than f of y. All right, so if you can find a point x in I, and if the function value at this point x bounds all for all the four function values in the interval J, then this proposition P must be true. Now, what is the negation of the statement? So this is negation. Therefore, for all x in I, there is y in J such that f of x is less than equals to f of y. This statement must be the negation. So, which is the opposite? So in this case, so in order the negation of P is true, then there must be a point in interval J, and the function value at this point bounds all the function values in the other interval I. Right? So therefore, no matter which interval I and J you have chosen, either one of these must be true, right? Okay, now what? We divide the interval AB into two closed intervals of the same lengths. So this is the interval A, comma B, and we divide it by half. Now we have the same intervals, and the interval on your left is going to be called I, and the interval on the right is going to be called J. So I is the interval on the left. Yeah, I know this is not very mathematical statement, but yeah, sorry about that. Yeah, but J is the interval on the right. Okay, so now we have two intervals I and J. Therefore, for these given intervals I and J, either one of these must be true. Okay. So if I is true, then we let I1 is I. And, no. If the negation of P is true, then we will let I1 is J. Okay, yeah. So what does it mean? So I'm going to draw a picture. This is A, and this is B, and I have a function. Okay, say that this is the graph of y equals to f of x. And what you're gonna do this? Yeah, we divide this whole interval into the same intervals. And this guy is called I, and this guy is called J. And based on this picture, I could find a point in I, point which is this point, and this point, the function value at this point bounds the function values on the interval j, right? So in this case, instead of this guy, this proposition is true, right? P is true. Therefore, this interval I is going to be called I1. Okay, and so this guy has been chosen, and this guy will be dropped now out of consideration. Okay, now what? I'm going to apply the same procedure. So this is I1. Yeah, I'm going to apply the same procedure to this interval. What do I mean by that? Again, I'm going to divide these two intervals into two the same intervals. And this guy will be called I, and this guy will be called J. So this is I, and this is J. This is I, and this is J. And now we have again, we have two pair of intervals I and J, one more time. And for these I and J's, which one do you think is true? In this case, well, not P is true because, well, I can find a point Y in J, which is this point, and the function value at this point bounds the function values in the other interval I, right? Okay, so this one is chosen, and this guy, this time around, I'm going to say this is I2. Okay, yeah, I know this is getting a little tedious, but just one last time. Now, I'm going to do the same trick, apply the same arguments to this interval. I will divide this interval into these two. And in this case, not P is also true, right? So therefore, this guy is going to be I2. So it goes like this. So applying the same trick, same argument again and again. So we're going to get a sequence of closed intervals. Okay. So applying the same procedure on I1 and choose I2 and continuing like this, we have a sequence of closed intervals. Okay. Okay. Oh, and just one more observation. So suppose that we were able to choose the sequence of closed intervals. And this statement must also be true. So therefore, the sequence, this sequence always contains the interval I always contains the point on where f attains its maximum, right? Therefore, for any n, if you choose any random point outside of this interval, then you must be able to find a point in this interval, and then the function value at this point is greater than that point. So so for any n, any positive integer n, the following is true. For every x in AB. And if x is not in IN, then there is point in IN such that f of z is greater than f of x. Okay. Because of the construction of these closed intervals. Okay. Okay. Well, now we go back to the sequence of these closed intervals. This is clearly a nested interval, right? So it's like getting smaller and smaller, and eventually the length of this closed interval is tending to 0, right? So because of the nested interval theorem, there must be one unique point in the infinite intersections of these intervals. By the nested interval theorem, there is a unique point C in this infinite intersection. 여러분 이 느낌표가 there exist 옆에 느낌표 붙으면 이게 uniquely exist라는 뜻이에요. 네. Here and okay, and what do you think this point C would be? Because IN always contains the point on where the function f attains its maximum. Therefore, I have strong feeling that this point must be the maximum that we are looking for. Okay. We will show that f attains its maximum at C. Okay, all right. Suppose not. So that is, well, suppose that this point is, the point C is not the point where f attains its maximum. Then you can find another point other than C such that f of x is greater than f of C, right? If C were not the maximum, then you can find such a point x0. Okay. Now, I'm going to derive a contradiction. We let epsilon to be f of x0 minus f of C over 2. This is still positive number. And since my function is continuous at this point C, at this point, so there is a delta such that if x is in the delta neighborhood of C, then f of C minus epsilon is less than f of x is less than f of C plus epsilon. And for this side, I replace this epsilon by this. Then this is minus C. So this is just, as before, this is f of x0 plus f of C over 2. This is just the midpoint between f of x0 and f of C. And clearly, this is less than f of x0. Sorry. So on this interval, the function values are always less than f of x0. Okay? So now, if you choose sufficiently large positive number, then this closed interval, this is just some, well, this is the IN. This IN, this closed interval, is from the sequence of the nested sequence of the closed intervals. And well, this IN must contain C because C lies in this infinite intersection. And IN is, well, but the length of IN is, is decreasing exponentially. So therefore, for sufficiently large n, this IN could be contained in this open interval from C minus delta to C plus delta, right? Because this is the interval of fixed length, and IN is decreasing exponentially. So eventually, at some point, IN must be contained in this interval. Okay, is it a contradiction? Oh, yeah. Then now this is a contradiction. Okay, so since we have chosen sufficiently small IN, so I guess it is okay to assume that this point x0 is, well, since x0 and c, they are different, so x0 is not in IN. Therefore, and f of z is less than f of x0 for all z in I. Why? Because IN is contained in this interval, and on this interval, function value is always less than f of x0, right? So therefore, every point in IN the function value must be less than f of x0. Is it a contradiction? Yeah, this is absolutely a contradiction because, I told you, if for any number that is out of IN, then you must be able to find a point z whose function value is greater than this guy. But in this case, even though this guy was out of IN, but I was not able to find such a point z in IN, right? And this is a contradiction. All right. So therefore, this point must be the maximum point of function. Maybe. Okay, great. All right, good. And this proves the extreme value theorem. Technically, we have proved that f attains its maximum on this interval, and I haven't talked anything about the minimum, but you can apply the same trick, the similar trick, and you can also prove that there is a minimum on this interval. So I'm gonna leave the proof. All right, and there is a little bit of corollary. F is this time around, F is continuous, but not on closed and bounded interval, but open interval. FAB. And suppose that f of x tends to infinity, positive infinity, as x tends to each of these endpoints. Oh, okay. So in picture, this must be something like this. So it looks like I have two vertical asymptotes. This is A and this is B, and no, I messed up. So this going to be the picture. This is the graph of the function that we are talking about. So, well, so as I approach to this end point, it goes to positive infinity, and for the other end point, I also have the function also goes to positive infinity. Then, under this assumption, then f must attain a minimum value somewhere between a and b. Yeah, which looks quite obvious from the picture. But yeah, how do I provide the proof of this? This is the silly exercise. Well, as x is approaching to a from the right, and f of x is tending to positive infinity, so that means for any sufficiently large positive number m, there is a delta, I would say delta 1, such that if x is between a to a plus delta 1, then f of x is greater than m. Okay? Likewise, so as I approach it to b from the left, and also function is tending to positive infinity, so that means there is a number delta 2 such that if x is between b minus delta 2 to b, then f of x is greater than m. So these two things, they can be considered as the definitions of tending to positive infinities. So, well, in this picture, suppose that this is our m. If this is m, then on this interval, we know the function values are greater than m, right? So this length from here to there, this length would be our delta 1. And on this interval, function value is greater than m, so therefore this length would be our delta 2. Okay? Okay, all right. Okay, now the proof is clear. Then we apply the extreme value theorem on a plus delta 1 to b minus delta 1. Not delta 1, delta 2. Sorry. So basically, we are talking about these closed intervals. This is a closed interval, and because of the extreme value theorem, you must be able to find a minimum number on this interval, and that minimum number on this closed and bounded interval can also be considered as a global minimum of the function on this open interval from A to B. The minimum of f on this interval is the minimum on AB. Okay. And this ends the proof. Okay. All right. Okay. So this is the end of the intermediate and extreme value theorem. And now we're turning to the next section. which is about the compositions and inverse functions. What is a composition function? 한국말로 합성함수죠, 그렇죠? 합성함수 모르시는 분 없을 것 같아요. Okay, composition function. Okay, this is the definition. I have two functions, f and g, and the range of g, suppose that the range of g is included in the domain of f. Then we can compose these two functions, and composition of two functions is defined like this. This is what we call, we have to compose the two functions. Okay, not a big deal. Yeah, I will pass. And oh, no. There is a very important deal. So if you compose two continuous functions, then the resulting function is also continuous. So in picture, so I have, well, this is, no. So this is x, and this is y. So we have function, this which defined on the y coordinate. So this is given by y coordinate. This is function g, and this is the function f, and say that this is c. Then this is f of c. Then this is g of f of c. And suppose that f is continuous at this point, and if g is continuous at this point, then this composed function, g of f, is continuous at this point. This is what you're supposed to prove. Okay. Okay. F is continuous at C. So this means for any epsilon, there is a delta 1 such that if x minus c is less than delta 1, then f of x minus f of c is less than epsilon. And g is continuous at f of c means for any epsilon, there is another number, say delta 2. And if y minus f of c is less than delta 2, then g of f of c minus g of y is less than epsilon. Okay, so these are two assumptions. Okay, now carefully combining these two, now I want to prove that this composed function is continuous. Oh, okay, all right. So choose any epsilon. For this given epsilon, well, since g is continuous at f of c, I can find a number, delta 2, satisfying this. Okay, yeah. Okay. Then for this given, well, so we found this delta 2, and I'm going to use this delta 2 as an epsilon over there. What happens if I this epsilon by this delta 2? Then for this given delta 2, I can find delta 1 such that if x minus c is less than delta 1, then f of x minus f of c is less than delta 2, right? Yeah. Okay. Now, can I combine this? Oh, okay. Right. Yeah, I'm done. I think I'm done. Yeah. Yeah, I have chosen any epsilon. And well, using this delta 2, then we know that there is a number delta 1. And if x and c, if they differ by less than delta 1, then f of x and f of c, they are less than delta 2. And we replace this y by f of x, then f of x minus f of c is less than delta 2. Then g of fx minus g of fc is less than epsilon because of this, right? So for any epsilon, I could find a delta 1, and if x and c is less than by delta 1, then this guy minus this is less than epsilon. And this proves that composed function is also continuous. So g of fx is continuous. Let's see. Okay, we are done. All right, and now we are ready to discuss the inverse function. Suppose that we have this weird property. Well, if x1 is different from x2, then the function value at x1 is also different from x2. Function value g of x1 is differs from g of x2. So this means there are no two distinct elements from the domain that has the same function values. In other words, looking at the function values, now then you can recover the point in the domain that attains that function value, right? This is the meaning of the definition. If a function has a property that different inputs always leads to different output. So that means looking at the function values, then you can reduce the domain of the element from the domain. So such a function is called the invertible function. And the inverse of f is defined in words. Well, but I don't like using words. So, well, this is our definition. So f is inverse of g, which is defined to be f of g should be identity, and g of f be also, well, if f satisfies these two conditions, then we say f is the inverse of g and denoted by g to the negative one. Okay, good. All right. So this is sort of very set theoretical definitions of the inverse function. 이 정도는 뭐 집합과 명제 단원에서 볼 법한 그런 데피니션이죠. 그렇지만 우리 이제 리얼 밸류 펑션 간에서의 인버스 펑션에 대해 관심 있는 거잖아요. 이쪽엔 캘큘러스 학생이니까. 여러분 거기 역함수를 가지고 있는 리얼 밸류 펑션들은 그래프가 어떻게 생겼을까요? strictly increasing 하거나 strictly decreasing 하거나 둘 중에 하나겠죠. 그래서 우리 페르시메 캘큘러스에서 인버터블 함수들은 increasing 하거나 decreasing 함수라고 보시면 되겠어요. 왜 이렇게 안 나오냐? Okay, so this is the definition of increasing function. If a is less than b, then f of a is less than f of b. So this is the increasing function, and decreasing function is defined like very similarly. And non-decreasing and non-increasing function is slightly relaxed condition compared to the increasing or decreasing functions. And these functions are called the increasing or decreasing function is called the monotone function. The functions that are either increasing or decreasing are called the strictly monotone function. And that are either non-increasing, non-decreasing called the just monotone function. All right. And the last theorem for today's lecture is going to be this. The inversion theorem. So what does it mean? It says if your function, suppose that you have a invertible and continuous function, then since the function is invertible, therefore the function must have the inverse function, and the inverse function is also going to be continuous function. This is the inversion theorem. Okay. Okay, what now? Okay, the proof. So we will show that f inverse is continuous on sorry. There are two kinds of inverse functions, invertible functions. F must be either strictly increasing or strictly decreasing, but without losing too much generality, we are going to assume that f is strictly increasing function. Sorry. Yeah. WLOG. Assume that f is increasing. In this case, well, we will show that f inverse is continuous on this interval. No, sorry. Yeah. So since I need this closing, I'm going to show that f inverse is continuous on this interval. Okay. Choose any epsilon. Then we divide the interval a comma b into n subintervals of lengths less than epsilon over 2. So it's going to be like this. This is a strictly increasing function. This is A, and this is B. And this is the graph of y is f of x. And because of our assumption, this is an increasing function. And I am going to divide the interval a comma b into n little pieces. And so that length of each subinterval is less than epsilon over 2. So just like this. So 1, 2, 3. Their lengths might be different, but what really matters is that each of these lengths, they are less than epsilon over 2. And yeah, for simplicity, I'm gonna call this guy A0 and this guy A1, A2, and this is AN minus 1, and this is AN. And say that these are n subintervals. Okay, since we divided this domain into n little pieces, and therefore this is gonna give us the division of the codomain. Like, yeah. Not good. Okay, so this is FA0, and this is FA1, so and this is f of AN. So this gives us, so FA from FA0 to FAN gives us the subdivision of the interval FA, F of FB. Divide the whole interval FA, FB into n subintervals. Okay. So we have the n subintervals for the domain, for the codomain FA, F of B. Now, since now we have n such a small intervals, but there must be a one subinterval whose length is the smallest. And we're going to call that length delta. Let delta be the smallest length of FAI minus 1 and FI. Okay, yeah, now we are ready. Then choose also let we choose two arbitrary points from the interval fa comma f of b such that y1 minus the distance of y1, y2, they are less than delta. Okay, so in this picture, we are about to choose 2 points from the codomain, and y1 and y2, they are separated by less than delta. And delta is the length of the smallest subinterval. So, well, in this case, we can consider two possibilities of the choice of y1 and y2. Either the case number one is y1 and y2, they are in the same subinterval, right? Or case number two is y1 and y2, they belong to two adjacent subintervals, right? Because y1 and y2, they are separated by at most delta. So either they belong to the same interval or they belong to the two adjacent intervals. But in either cases, in both cases, then either number one, y1 and y2 are in the same subinterval, or y1 and y2 are in two adjacent intervals. I should say subintervals. Okay. If the case number one is true, then f inverse of y1 minus f inverse of y2. Okay, suppose that y1 and y2, they are in the same subinterval. But then if y1 is here and y2 is there, then f inverse of y1 will be here, f inverse of y2 will be there, right? Then distance between f inverse of y1 and f inverse of y2 must be less than length of this interval, right? So this means their length is, they are separated by less than epsilon over 2, which is the length of the one single interval. Well, what if the case number 2 is true? In this case, if suppose that y1 is here and y2 is there, then the f inverse of y1 will be here and f inverse of y2 will be there. I mean, they are separated by, their separation length cannot exceed the length of these two intervals, which is epsilon, right? Is epsilon. So therefore, in both cases, f inverse of y1 minus f inverse of y2 is always less than epsilon. What does it mean? So for any epsilon, I could find the delta, and if y1 and y2, if they are separated by less than delta, then function values of y1 and y2, they are separated by less than epsilon. So this means the function, the f inverse, is not just merely continuous, but actually f inverse is uniformly continuous on this closed interval. But you know, the being uniformly continuous is stronger condition than the just being merely continuous. Therefore, this proves that f inverse is just continuous function. So this ends the. All right. Yeah. I really appreciate your patience and see you next.